discuss about transformer. Transformer is a static device which can transfer electrical energy from one circuit to another circuit without any physical connection between them by changing the level of voltage at unchanged frequency. Because it transfers electrical energy, that is why it is known as transformer. Now, what is the one circuit and another circuit? In this case of transformer, there are two coils. This one coil is this, another coil is this. This coil is known as primary side, whereas this coil is known as secondary side. When input is connected in this winding, then this winding is known as primary winding or primary side. When output is taken from here, then it is considered as secondary side or secondary winding. But in case of transformer, there is no primary and secondary. Why? Because when we connect input from this side and we are getting output from this side, then it will become primary, whereas it will become secondary. Here E1 is the EMF induced in primary winding, whereas E2 is the EMF induced in secondary winding. And this is known as self-induced EMF, whereas this is known as mutually induced EMF. Now, this is a constructional view of transformer, and here the flux is developed in the core of the transformer due to current in primary side, and this flux is linked with the secondary winding as well, and hence causes the mutual induction. Here mutual induction means due to the rate of change of flux d phi by dt, EMF will develop in the secondary side, and which is considered as E2, and hence we can say E2 is proportional to d phi by dt. Now, considering the electrical symbol of the transformer, this is the electrical symbol of transformer. This side represents primary winding, whereas this side represents secondary winding. The two lines between the two windings is known as core. It represents transformer winding is placed over a magnetic core, primary as well as secondary. Here the supply is AC, whereas the load is connected to the secondary side. This load may be R, this may be RL, this load may be R, L and C, any combination of the load. Now, working principle of a transformer, the phenomena in which whenever a conductor is placed in a magnetic field, an EMF is developed across it by mutual induction. Mutual induction here means if there is some current in the primary side, then due to the flux develop that current, the EMF will develop in the secondary side as well. The magnitude of that EMF is directly proportional to the rate of change of flux linkage. We know E is proportional to d phi by dt linkage, and the number of turns, because there is a proportionality factor, and this can be written as E is equal to n d phi by dt, and the sign of this can be taken by Lenz law, which is minus, as according to Lenz law it always opposes the cause producing heat, and this phenomena is known as electromagnetic induction. In this way we can say electromagnetic induction has three parts. One, it is the mutual flux development in flux in one core and linking with the another core. Then EMF developed in the secondary because of the rate of change of flux linkage, and the magnitude of that EMF is always defined by the number of turns. Now, considering the construction part of the transformer having different parts. The first one is considered as magnetic core, where the windings are placed, is known as magnetic core. It is generally made of soft iron, soft magnetic material like silicon steel with very thin laminations. Primary and secondary winding. Windings are nothing but the conductors, and either they made of copper or aluminium. Now, they are copper and aluminium wound over the magnetic core. The coil connected with the supply is known as primary winding, which is connected to the load is known as secondary winding. Terminal insulators. We know the transformer, we have to connect input and we have to take output. These output is not directly connected with transformer, we are connecting through a terminals. These are the three terminals if it is three phase transformer. Now this winding goes to the these terminals goes to the transformer. High grading insulator used for the connection of transformer winding with the power lines. Now the important part of transformer is insulation. In electrical engineering, the major challenge is insulations only. Now, we need to provide insulation between magnetic core and winding because transformer core, suppose this is a core of the transformer and windings are placed at this part, and we do require, because winding is having some current and potential applied across it, we do require insulation between this core and winding. This is the first part. The insulation between inner turn of the winding. There are two turns of the windings, and between these two turns, let it is first, it is second, and in between these two turns, we do require insulation. The insulation between transformer body or tank. Now the transformer is, all these components are placed in a tank, and hence we do require insulation between this tank and rest of the part of the transformer. Now, oil tank with cooling arrangement. As we know, this is the pictorial view of transformer. This is cut section. Here we can see these are the three windings, winding 1, winding 2 and winding 3. Corresponding to these three windings, there are three terminals, 1, 2 and 3. Now, the transformer core and winding of a transformer are usually placed in an oil tank. This is a tank. Since oil is filled in it, that is why it is known as oil tank. Transformer is specially prepared high grading insulation oil, and the oil inside this transformer is a special type of oil, is also known as mineral oil. During operation of oil also serves as cooling agent. Why do we require oil? This is not only providing the insulation between the transformer and tank and core of the transformer and winding of the transformer, it also serves as a cooling agent. Why? Because the when transformer is subjected to some load, it, it gets heat up, and because of that heat, the oil within this transformer tank, it gets expanded. This expansion of this oil will be circulated through these ducts. These are the ducts from where oil can be circulated. The cooling arrangement can be used as forced, fan or natural. Natural here means the circulation of this oil, whereas we can connect external fan for cooling of this transformer. Because when load is connected to this transformer, very high current will flow, and this high current will cause I square R loss. And this I square R loss is nothing but a heat in electrical system. Now another important part is conservator. Over the transformer tank, there is another tank. This is either it is partially filled or it is half filled. But when this transformer is getting heat up, that the oil will be changing its temperature, then due to the expansion it requires some space, and this empty part of this conservator will provide that will serve that purpose. Now this expanded oil will move to the conservator and circulate through these ducts and keeping the transformer protected. Now breather, there is one more component associated with the transformer tank, that is breather. Breather is another small size of tank in which silica gel is filled, and this silica gel, the purpose of having this silica gel is to absorb the moisture content, because in case of transformer, moisture is the major challenge. If there is small moisture content in the transformer oil, it may break down the insulation capacity of the transformer oil, and hence it becomes necessary to absorb that moisture content time within the time period. And silica gel having a special property, it changes its color from pink to blue when it absorbs the water contents, and we will get to know whether a transformer tank is having some moisture content or not. Now Depending upon the application of transformer, transformer can be classified in three ways. The step up transformer, step down transformer, isolation transformer. Step up transformer. Step up transformer here means when output voltage is greater than the input voltage, because applied voltage is V1 and whereas the output voltage we are getting at the secondary winding is V2. If V2 is greater than V1, that transformer is known as step up transformer. Whereas when V2 is less than V1, that type of transformer is known as step down transformer. There is a special use of transformer where V1 is equal to V2. Neither it is greater than or nor it is less than the secondary voltage. And that type of transformer is known as isolation transformer. In that case, the purpose of transformer is to isolate two different circuits like that. One part is this, another part is this. There is no physical connection between the two, and hence if we want to remove the secondary part, then we can easily remove from here. This is a special type of application of transformer. Now whereas in case of classification, as far as the classification is concerned, transformer can be having a two type of core. One is the core which is having separately placed with windings. One is the primary winding, another the secondary winding. If individual part of the winding is placed an individual part of the core, then it is known as core type transformer. The transformer in which there is a single path for the resultant flux is known as core type transformer. Whereas there is another type of construction of transformer core in which the total flux phi developed in one winding is divided in two parts. One is here it is phi 1 let and here it is phi 2. This total flux will be equals to phi 1 plus phi 2, and the transformer in which there are two paths for the resultant flux is known as shell type transformer. This is a shell type transformer. These are the pictorial view of core type and shell type transformer. This is core type and this is shell type transformer. Now, core design. Transformer core is not made of a solid material like this. This is a solid material, and this cut section inside this we are having a space and windings are placed at this point. If it is, if you are placing winding V1 and similarly V2 in this side V2 over the single core having solid structure. In that case, some because this core is also a complete path and some current will start flowing within this core also, and that current is known as eddy current, IE. Because of this eddy current, this because this core is having internal resistance R, then there will be I square R loss, and these losses will hit up this transformer core, and this is known as eddy current loss. This eddy current due to the loss due to eddy current is known as eddy current loss, and they may cause extra heat in the transformer. To avoid this heat, then we have to divide the core of the transformer in such a way that there are very thin layers. Now, like that. Instead of having a single magnetic material, we are having a number of thin layers, and these thin layers are riveted at this point, and this is known as laminated core. Transformer core is not always a solid structure, it is always a laminated part having very thin laminations and also known as laminated core. Transformer core material is selected based upon the thin hysteresis loop. Hysteresis loop here means the soft magnetic material or hard magnetic material. Soft or hard magnetic. Soft magnetic material here means This core can be easily made magnet and can be easily demagnetized. Whereas hard magnetic material here means the transformer core, once it is made magnet, it will be having some residual magnetism within it when demagnetizing is applied. And the most commonly used material is cold rolled grain oriented silicon steel, also known as CRGO silicon steel. This is a specially designed structure of the transformer core. Now, considering the transformer, apart from the constructional component, then we can analyze the transformer electrically. A transformer is said to be an ideal if resistance offered in the winding is zero and the flux developed in the primary winding links totally with the secondary winding. This means the internal power in the transformer as a loss is zero, the input power in the primary winding will be equal to the output available at the secondary winding. We know by the definition power input is V1 into my I1 and power output is V2 into my I2. Now, because this is a AC supply, the power we can consider V1 I1, V1 I1 cos of theta 1 must equals to V2 I2 cos of theta 2. Now, considering cos of theta 1 and cos of theta 2 equal, then also we can say the input power V1 I1 must equal to V2 I2. Now, the circuit diagram, from the circuit diagram, if we apply V1 equal to the back EMF, that is the primary induced EMF, we have already discussed, this is V1, the EMF developed in this winding is E1. Similarly, we are having E2 in the secondary, then terminal voltage is V2. Now, considering V1 equals to E1 whereas V2 equals to E2, because there is no drop in within the transformer winding and transformer is considered as an ideal transformer. Now, this is rearrange this equation, then it will be V1 upon V2. V1 upon V2 will be equals to I1 will go down over here, then I2 upon I1, because V1 and E1 both are equal and hence replaced by E1. V2 and E2 both are equal and hence replaced by E2. By the definition, we know E1 is proportional to N1 and E2 is proportional to N2. Therefore, we can say V1 by V2, I2 by I1 must equal to E1 by E2 is equal to N1 by N2. Here N1 by N2 is defined as the turn ratio of the transformer, whereas V2 by V1 is defined as a transformation ratio as the transformer. Transformer ratio here means the concept of transformer, changing the level of voltage. Ideal practical ideal transformer can be having a very high efficiency and let's say 98%. The practical transformer cannot be ideal, but there will be some losses and we'll consider at the later stages. Now, in case of transformer, we know the AC supply, input supply is AC, and when AC supply is connected across a transformer, the magnitude of the EMF developed in the winding can be calculated. This is E2 and this is E1. Now we know flux developed in the transformer winding due to AC supply is phi is equal to phi m sin omega t. Because of AC supply we know I is equal to Im sin omega t, and because of this current if flux is developed phi, then it will also be a phi m sin omega t. Now, considering flux developed in the winding is phi m sin omega t, we know E is equal to minus n d phi by dt, putting the value of phi over here and then differentiating this function and rearranging as a sign of quantity, then the resultant value will be 2 pi f n phi m sin omega t minus pi by 2. It means the EMF developed in the transformer winding always lags the flux by an angle of pi by 2. Now, if this is the phasor of flux, the EMF will be E will be here by an angle of 90 degree lagging. If we have to plot over here, then it will becomes leading. But in case of transformer, it is not leading. Now, considering this part is constant because 2 pi f supply frequency is constant, number of turns once the transformer design is constant, the maximum value of the flux also remain constant. And hence we can say this component is nothing but the maximum value of this quantity, E. Comparing with standard, in standard we are having E is equal to Em sine omega t minus pi by 2. Now it means Em is nothing but equals to 2 pi f phi m. Now we know this is the magnitude maximum value and RMS value is Em maximum value divided by root 2, and hence it is 2 pi f phi m divided by root 2, and simplifying this function it will be 4.44 phi m f n. Now, if the EMF developed in the primary side, it is represented as E1. If the EMF is developed in the secondary side, it is represented as E2. Now, we know E1 is depending upon flux. Flux is the common in the both the windings. Supply frequency is same in the both the winding, and hence phi m and f will remain same. But in primary side, the number of turns may be different, whereas in secondary side, number of turns may be different, and hence we can say E1 is proportional to N1 and E2 is proportional to N2. And taking the ratio of these two, then E1 by E2 it must equals to N1 by N2. The transformer can be analyzed when transformer is at no load, when transformer is at load. In this case, here we consider there is no load at the transformer. If I connect some load, that load here means R, RL, RC, RL and C. Any combination of load can be connected on the transformer.